Now I think we need to talk about what causes objects to rotate. We have a little bit of intuition about this. Let's take a look at a door. This is a top view. So here's the hinge, and there's the door. And we're looking down, top view of the door. It's hinged on the left. And you're trying to walk out. Maybe you're trying to leave the classroom. The door has a hinge on the left, and you're trying to go through. Where are you going to push on the door? You have a number of options. You can push right here. You can push over here. You can push in between. You can push at some angle. How are you going to push on this door to get it to rotate as quickly as possible so you can be on your way? Well, I think we all know the answer to that. You're going to push perpendicular to the door at the end furthest from the axis of rotation. Now let's see if we can quantify that a little bit. What you're doing with this force is you're producing torque. Torque is what causes rotation, and we produce torque by applying a force at some perpendicular distance to the axis of rotation. So the torque, tau, the Greek letter tau we use for torque, it's a vector quantity, and the magnitude is going to be the force times the perpendicular distance to the axis of rotation. We call that the lever arm. Force times the lever arm. Another way to think of it is it's the perpendicular force times the distance to the axis of rotation. And let me go through a couple of examples and show you the two ways to think about it. Let's take a look at these different cases. So in example 1, we're trying to find the torque. And the torque is the force times the lever arm, the perpendicular distance to the axis of rotation. And in this case, it's just the length of the door. I'll call that L. So the force is just F. What do we do to find the lever arm? You extend the line of force, and you find the perpendicular distance. I'll draw it in red here. The perpendicular distance from the line of the force to the axis of rotation. In this case, it's L. So for case 1, this is just going to be F times L. Let's take a look at case 2. Let's say that this is 3/4 the length of the door, and our angle is, what should our angle be, 30 degrees? So in case 2, the torque is going to be F times the lever arm. We extend the line of force. I'll draw it over here. We extend the line of force. We find the perpendicular distance to the axis of rotation. That is our perpendicular. The torque is F times the lever arm, our perpendicular. I've extended the line of force out. And then we found this red line, the perpendicular distance from the line of my force, the dashed line here, to the axis of rotation is my lever arm, our perpendicular. And we could look at that two ways. We could look at that as the sine of 30 degrees or the cosine of 60 degrees. What is our torque? It's F times 3L over 4 sine 30 degrees. So that's the lever arm method. We could also say the torque is F perpendicular times the distance to the axis of rotation. Let me redraw my door. The force was being applied out here at 3/4 the length. I'm going to draw my force vector on this side because I want to break that vector up into two other vectors. One that is parallel to the line that goes to the axis of rotation, and one that is perpendicular to the line that goes to the axis of rotation, and that means the red line here. So parallel to the red line and perpendicular to the red line. And you can see that the parallel component of the force, if I were to extend that out it would pass right through the axis of rotation. It produces no torque. All the torque is produced by F perpendicular. What is F perpendicular? It is F times the sine of 30 degrees. So what is this? It's F sine 30 times R. What is R? 3/4 the length of the door. So you can see we get the same thing. Doesn't matter if you think of it in terms of R perpendicular, the lever arm, or if you break up the force into a component that produces torque and a component that does not produce torque, and you use the second approach. You get the same result either way. So how do we use this to figure out what the rotation is? Well, with forces, what did we say? We said force causes motion. And what did we mean by that? The net force caused acceleration, F equals ma. So now what we're saying is we're not using force anymore. We're using torque for rotational motion. The net torque causes rotational motion. And instead of m, we have a rotational inertia. And instead of a, we have a rotational acceleration, angular acceleration, alpha. So the net torque is equal to I alpha. I should make a note about vector quantities. Theta, omega, and alpha are what we use for kinematics and our rotational motion. And omega and alpha are vector quantities, as is torque. Just like velocity and acceleration and force, those are vector quantities. For linear motion, we always said choose the direction as positive, whatever makes sense to you for the problem, and be consistent. And I don't know why we've all of a sudden changed when we get to rotational motion, and the textbooks always define a certain direction as positive. Personally, I say pick whatever direction you like to be positive, what makes sense for the problem to be positive, and be consistent. But because we like to measure angles in math classes on a coordinate system where the positive angle is measured with respect to the positive x-axis, and as theta increases in a positive manner, this line would sweep out a circle in a counterclockwise direction. Theta would go counterclockwise, like I've drawn here, to give us a positive angle. So we always choose in physics textbooks counterclockwise to be our positive direction for omega, and any torque that would cause something to rotate in a counterclockwise direction we would view as positive torque. If something is rotating clockwise, we would call that the negative direction for omega. And for torque, if it would cause rotation in the clockwise direction, we would call it negative torque. Alpha, it just depends on whether it's causing the object to increase its speed or decrease its speed and what direction omega is. You have to look at both of those. But I say choose whatever direction you want to be positive, be consistent. It doesn't have to be clockwise, counterclockwise, but that's the way your textbook is probably going to do it. They will probably always use counterclockwise as positive, clockwise as negative. The other thing that we do to define the direction of the torque is we use what we call a right hand rule, where we place our thumb of our right hand along the axis of rotation, and then we kind of roll our fingers on our right hand in the direction of the rotation. Let's say I have a door, and there's my axis of rotation, and my door is rotating counterclockwise. I put my thumb up out of the page along the axis of rotation, and my fingers would roll around or curl around in the direction that the door is rotating. I would say omega is pointed out of the page because this door is rotating counterclockwise, and my right hand would make my thumb pointing out of the page. So I would say omega is out of the page, toward you, out of the page. If the object was rotating clockwise, in order to get my fingers on my right hand to roll and curl and point in the direction that this object is rotating, in the clockwise direction, my thumb has to be pointing into the page along the axis of rotation. So I would say omega is into the page, in this case, for a clockwise rotation. And when you use those terms, then it doesn't matter where you're located. Let's pretend for a minute you and a friend were facing each other, and there was a bicycle wheel spinning in the middle between the two of you. One of you says it's going clockwise, the other one would say it's going counterclockwise, right? You don't, those terms don't work when you've flipped around and you're looking at it from the opposite side. But both of you, using the right hand rule, would have the direction of omega pointing in the same direction. So it's a very convenient system so that everybody knows what they're talking about.